Here's a conductor with a cross-sectional area of A and a total length of L. And in this case, the conductor has positively charged mobile particles that can constitute an electric current if all these charges were adrift due to an electric field. Okay, let's come up with some other variables. Let's say we take a little segment of volume. The total volume of this whole cylindrical conductor obviously would just be A times L. So this little segment represents some fractional amount of the volume. Well, if we take a measure of how many of these particles are inside of that fractional volume, then we can come up with a density of free particles that we'll symbolize here with lowercase n, and we'd say that would be equal to the number of particles in that small fraction of volume, and so we could get an idea of the number of particles per cubic meter. So it represents the density of free charges. Now if I want to get a sense of how much charge overall is in this cylindrical conductor, then I suppose I would need to multiply the density of charges times the amount of charge per particle. Now if all of these were electrons, then we would know the charge per particle would be equal to 1.6 times 10 to the negative 19th coulombs, but I haven't made up my mind yet that this is a metal wire. In fact, I think I've decided that it's definitely not, because I am symbolizing the charge carriers as positive, and we know in a metal wire the charge carriers are negative electrons. Anyway, if we multiply the number of particles per cubic meter times the amount of charge per particle, we would still then need to multiply that times volume, which would be cubic meters, and so we would have the total amount of charge. Well, instead of figuring out the total charge in the whole conductor, let's figure out how much charge is inside just some small length of it. So maybe we call this dl. Starting to get messy, so I've got this drawn again. There's dl. We know the cross-sectional area, and it has some density of free particles represented as n. So the amount of charge in this shaded area we'll call dq, which represents a fraction of the total charge, capital Q. This would be equal to the density of charges times the amount of charge per particle multiplied by the volume. But the volume here would be A times dl. Okay, let's define electric current, symbolized by capital I. Electric current is defined as the rate at which charge flows or drifts through a wire. So it's not dq, rather it's dq dt. So the units we use to measure electric current are amperes, often just referred to as amps for short. And an ampere then must be equal to a coulomb per second. So if we know how to calculate the amount of charge in some fractional length of this conductor, now we imagine applying a potential difference. High potential at the left end of the wire, low potential at the right end. That creates an electric field excuse me, inside of the wire, and it causes these particles to drift. Now, I've oversimplified it and showed it as if all these positive charges are moving exclusively to the right. Truth is, they have random motion and they travel like this, then maybe collide. And so the motion overall particles zigzag around, but the net effect is that they're going to have a displacement to the right. So yeah, I'll symbolize their drift velocity as a bunch of little arrows pointing in the same direction. So now, whatever amount of charges occupy this fractional volume are going to drift out of there, and then a whole new set of them will drift in. So there's going to be a rate at which charges are passing through this length, dl. And at any instant in time, the amount of charge inside of that region is n times the charge per particle times the cross-sectional area times this fractional length. So the current then, because it's equal to dq dt, must be nqa dl over dt. Let's separate out the dl over dt. So we can say I is equal to nqa dl dt. But dl dt is nothing more than the drift velocity. So the current is equal to the density of free particles times the charge per particle multiplied by the cross-sectional area of the conductor multiplied by the drift speed. Let me turn this around. So we have high potential on the left end and low potential on the right end. The electric field still points toward the right, but now we are talking about a metal wire, and we can see that in this case the free particles are electrons, and now their drift speed is to the left. Well, it's still true that I is equal to n times q times a times drift speed, but in this case we know the value of q. It's 1.6 times 10 to the negative 19th coulombs per particle. And if you remember, this drift speed is typically on the order of magnitude of about 10 to the negative 4th meters per second. Let's double check these units one more time. So if we multiply n times q times a times v, we have particles per cubic meter times the amount of charge per particle multiplied by square meters multiplied by meters per second. Particle cancels out. Square meters times meters cancels cubic meters, and we're left with charge per second, or coulombs per second, which indeed is an expression of electric current measured in amps. 1 amp is the same thing as 1 coulomb per second.